I am Frank Potter, a physicist who is retired from the University of California at Irvine. However, my goal of better understanding nature's leptons and quarks of the Standard Model has only increased over the years as we accumulate more experimental results from the many particle research groups around the world. Today, I thank the organizers of this Neutrinos from Home conference for the opportunity to discuss the reason for exactly 3 lepton families and the rationale for family mixing. In the short allotted time of 18 minutes, we can just introduce and discuss the most important related ideas. So please realize that many important details may be briefly mentioned only. Up until now, we know that the Standard Model has at least 3 lepton families and 3 quark families, but the numbers of each are unknown. Each family has 2 weak isospin states, and each of these particle states in the normal space have the unique antiparticle states in the conjugate space. And Z0 decays have suggested that there are only 3 lepton families with particle masses under 90 GeV. From here on, we will consider only the lepton families and not the quark families. Although the Standard Model originally assumed the conservation of each lepton family number separately in weak interactions, the ability of one neutrino type to change into another neutrino type makes this property invalid. But why this neutrino mixing occurs is unknown. So, we know that the Standard Model neutrino weak isospin states are not the neutrino mass states. Also, the muon and the tau are not excited states of the electron. So, with 3 lepton families, we need 3 mixing angles for the PMNS lepton mixing matrix. We ask, how can we limit the number of lepton families? By placing all 6 leptons in a 6-dimensional irreducible representation of a single group, such as A5. Or there could be a geometrical symmetry limit, such as having our 3 lepton families represent the 3 discrete symmetry binary groups for the regular polyhedrons in R3. That is the real group in 3 dimensions, the real space in 3 dimensions, that have a 3D volume, also known as the modular double groups, and by these other isomorphic group names. That is, gamma 3 prime is A4 prime, is 2T is 332, or gamma 4 prime is S4 prime equals 2O, or 432. Or gamma 5 prime is A5 prime equals 2I equals 532. Our plan for the leptons is to assume that the conservation of total lepton family number, capital L, holds true, which is the sum of each of the 3 lepton family numbers. Then we assign the 3 modular groups that I will call by their alternative names 2T, 2O, and 2I to the 3 lepton families. By the Noether's theorem requirement of a continuous symmetry, we will then have a conflict with our 3 discrete symmetry groups. So they must act collectively in a linear superposition to mimic a continuous symmetry group. Let's try SU2, since they are binary subgroups of SU2. Several research groups suggest that modular groups and modular double groups would be appropriate for the lepton families because they agree with superstring approaches. Therefore, we assign the discrete symmetry modular double groups 2T, which is also gamma 3 prime, which is 332, to the electron family, 2O, which is the same as gamma 4 prime, or 432, to the muon family, and 2I, which is gamma 5 prime, which is also equal to 532, to the tau family. As you can see, 2T is the binary subgroup of SU2 for the regular tetrahedron. 2O is the binary subgroup for the regular octahedron and cube. And 2I is the binary subgroup for the regular icosahedron and regular dodecahedron. Thus, we are suggesting that the lepton families have the symmetries of the Platonic solids at the Planck scale. Why these groups? Well, invariant theory relates them to the elliptic modular function j of tau and its linear fractional transformations. Specifically, the j of tau is the ratio of W1 over NW2, where the W's are equations in two complex variables for the vertices and face centers of the regular 3D polyhedrons. The clue, however, lies in the values of n for each binary subgroup, values which appear similar to the mass values of the charged leptons in MeV over c squared. Incidentally, this mismatch of the two sets of numbers can be used to predict the off-diagonal elements for the charged lepton mixing matrix. In this table of the three lepton families that represent the three binary subgroups of SU2, we should remind ourselves that 2T is not a subgroup of 2O nor 2I, even though their group orders might suggest such a possibility. To conserve total lepton family number, big L, capital L, we need to make the three discrete symmetry subgroups collectively act to mimic the continuous symmetry group SU2. We will use the three quaternion generators for each subgroup. Recall that a quaternion represents the location of a point in R4, the real space of 4 dimensions, as well as a double rotation in R3. Here we express the familiar three Pauli generator matrices for SU2 in terms of the three quaternion generators I, J, and K. Only the U2 generators in each subgroup, that is the 2T, 2O, and 2I, is not the same as the corresponding SU2 K generator. So we must make the sum of their three U2 generators equal to the generator K for SU2. Thus, we have three equations for three unknown factors. In this table, we showed the three U2 quaternion generators for our three lepton family groups. The resulting three normalization factors, or normalized factors from the three equations, and their corresponding double angle values in degrees. The factors give the projections onto the k-axis. Being factors for quaternions, we must take their half-angle values. The half-angle values, theta 1, theta 2, and theta 3, are listed in the last column. Theta 1 is 52.660 degrees, theta 2 is 18.379 degrees, and theta 3 is 61.238 degrees. The absolute values of the differences of the half-angles are the absolute values of the mixing angles for the 3x3 lepton mixing matrix. So theta 1, 2 is 34.281 degrees, theta 2, 3 is 42.859 degrees, and theta 1, 3 is 8.578 degrees, all in the first octant. This table shows that our mixing angles agree with the experimentally determined values quite well. Note that we have all three mixing angles in the first octant, even the theta 2, 3 value, which is 42.85 degrees. Some analyses of the experimental data predict that theta 23 lies in the second octant with a value greater than 45 degrees. So therefore, we must wait for more data to resolve the issue of the theta 23 octant. The total 3 by 3 PMNS lepton mixing matrix is the product of the charged lepton matrix part and the neutrino matrix part. The charged lepton part is very close to being the unit matrix, which would have ones down the main diagonal and zeros everywhere else. So we will assume that the PMNS lepton matrix represents neutrino mixing only. Here is the neutrino mixing matrix. We can see that our predicted matrix elements derived from the linear superposition of our three groups, 2T, 2O, and 2I, fit very well within the ranges calculated by NuFit 5.2. Especially look at the 1,3 value for the comparison at the end of the first row. You see that the negative 0.1491 value would fit right within the bracket from 0.143 to 0.155. We don't have time to discuss the Dirac phase for CP violation, except to say that a value not equal to 0 or pi is acceptable, because it's related to the Yarlskog constant J, which would then be a non-zero value. And also there would be an asymmetry between leptons and anti-leptons. To calculate the neutrino mass values, one would follow the method derived from density matrices used by mathematical physicist Carl Brennan in 2006, that is listed as reference 10. From a one-circulant matrix, he derives the famous Noether formula for the charged lepton masses, then operates on the bimaximal mixing matrix approximation by using the modulus tau equal to exponential of 2 pi I over 3, which numerically equals minus 0.5 plus 0.866 I, exactly at the cusp in the complex fundamental domain for some modular groups, derives a matrix that is the 24th root of the unit matrix, counts for the Berry-Panchardinum phase in a mass operator, and then establishes the eigenvalue equation for the square root of the neutrino masses. In reference 11, we followed his method and calculated the neutrino mass values using our neutrino PMNS mixing matrix instead, and the best fit modulus value tau equal negative 0.496 plus 0.877 I, which is slightly off the cusp in that fundamental domain from its previous value that was used by Brennan at the exponential 2 pi I over 3. From the eigenvalue equation for the square root of the masses, we predicted the normal order of the neutrino mass values. M1 is 0.38 millielectron volts, M2 is 8.91 millielectron volts, and M3 is 50.62 millielectron volts, all of which are reasonable values. We need to wait for several future experiments to actually determine the true neutrino mass values. So what is the lepton mixing rationale? Well, the mixing satisfies Noether's theorem, so that conservation of the total lepton family number remains true. That is, capital L is L sub E, L sub plus L sub mu plus L sub tau. If you want to see how this would work out for the quarks, look at reference 8 for quarks in 4D and the CKM matrix. So why are there exactly 3 lepton families? Because they represent the 3 discrete symmetry groups 2T, 2O, and 2I in R3 that determine 3 correct lepton mixing angles. There are no more finite quaternion groups in R3 that have a volume. So we have a result that the leptons are not point particles. Plus, our result agrees with the Z0 decay results for approximately 3 families, as long as the mass values are less than 90 GeV. So let's review what we've achieved for the leptons. We've identified 3 discrete symmetry modular groups, which I'm going to call 2T, 2O, and 2I, that the leptons are 3D entities, essentially the regular polyhedrons in 3D. Collectively, they mimic SU2, and in this way satisfy Noether's theorem, from which we derive then lepton mixing angles. Theta 1,2 is 34.281 degrees, theta 2,3 is 42.859 degrees, theta 1,3 is 8.578 degrees. We also determine the 3 neutrino mass values, which fit within the ranges from the experimental results. So we can draw 2 major conclusions. There are exactly 3 lepton families because they represent 2T, 2O, and 2I. They produce the correct mixing angles when we use these groups, and these are the only discrete symmetry finite quaternion groups in R3 that contain a volume. Therefore, we know that leptons should probably not be point particles at the Planck scale. Our other conclusion is that lepton mixing of these 3 discrete symmetry binary groups satisfies Noether's theorem by mimicking SU2, so that conservation of total lepton family number remains true. These next 3 slides contain the references that are pertinent to the topics that I've discussed in this presentation. Thank you.